Okay, so now that we have a system in place that we can discuss elements and their properties, we're going to take a closer look at the periodic table of the elements. And the periodic table of the elements is structured the way that it is because of the periodic law. And basically, the periodic law is an illustration of the fact that if you put all the elements in order of their atomic number, starting with hydrogen at 1, and going forward, here we're going all the way up to calcium, you'll notice a repeating periodicity to the chemical and physical properties of the elements. The three that are highlighted here, lithium, sodium, and potassium. Lithium happens to be a solid at room temperature. It is a metal. It's very reactive, and it tends to lose one electron to form a singly charged positive cation. 8 elements later, we have sodium and A, which is also a solid at room temperature, a metal, and also is very reactive, and tends to lose one electron to form a singly charged positive 1 cation. Again, 8 elements later, we have potassium, a solid at room temperature, a metal, forms a +1 cation. You'll see this throughout the periodic table. From potassium on, the periodicity, the length in between the elements gets a little bit longer because of the D block elements, as we'll see later. But it is still there. We can look at any other elements, say helium. Helium is a gas at room temperature and very inert, meaning it is unreactive. It doesn't react with very much else. Neon, 8 elements later, is another gas at room temperature, very inert. 8 elements later, again, we see another gas, which is also very inert, argon. Okay, and so one of the first chemists or scientists to realize this was the famous Russian chemist Dmitri Mendeleev, illustrated here in a stamp commemorating him. He constructed one of the earliest periodic tables of the elements, or the earliest periodic table of the elements, as a study tool for his students in one of his textbooks. And you can see an illustration of one of the early ones here. Here you can see the periodic law for lithium, sodium, potassium, and then followed by rubidium and cesium here, which we illustrated previously. He put the periods in a row, whereas now in modern periodic tables we'll see them as a column, but they're here nonetheless. He knew so much about the periodic law, he was able to predict spaces for elements. You can see here is a question mark, which he knew should be there based on the periodic law, just hadn't been discovered at the time of his development of the first periodic table. So a very powerful predictive method at that point in time. Here we can see a modern periodic table of the elements. We can see there's quite a few more elements that have been discovered since the time of Dmitri Mendeleev. And here we're going to illustrate the 3 broadest classifications of elements. We have metals, pictured here in light tan color, the nonmetals in the green color, and then the metalloids, which we'll discuss briefly, in the purplish color. Okay, you can see that the nonmetals are over here on the right side of the periodic table, and the metals are on the left side of the periodic table, and they constitute the majority of the elements. In the middle, we have our metalloids, pictured in purple again, and they are elements that sort of border the non-metal and metal characteristics. They share some characteristics and properties with metals, some with non-metals. So we sort of classify them as their own sort of in-between category, metalloids. So if we take a look at the properties of metals, many of these you should already know or have seen before. Metals conduct heat and electricity very well. They're reflective, meaning they have a shiny surface. They're malleable and ductile, meaning that they can be shaped or drawn or pulled into wires, which we know, of course, is true for metals. It turns out that most solids or metals are solid at room temperature, except for mercury, which is a liquid at room temperature. As we said previously, they tend to lose electrons to form cations, and as you saw in the periodic table, the majority of elements are, in fact, metals. On the right side of the periodic table, we find the nonmetals, and they are actually found in all 3 states. We have one of such: sulfur in solid state, bromine, it's in a liquid state, and there's quite a few that are in the gaseous phase, including chlorine. In contrast to the metals, they are poor conductors of heat and electricity. The solids are brittle, they are not malleable or ductile, and as we said before, they gain electrons in reactions to become anions, negatively charged ions. And in between the metals and the nonmetals, we of course had the previously mentioned metalloids, and they share characteristics and properties of metals and nonmetals. One such example would be silicon. It is solid, it is shiny, it conducts electricity, but does not conduct heat that well. It is brittle, not malleable or ductile. They're also known as the semiconductors because, of course, silicon, being the major example, is used quite a bit in the semiconductor industry, and they can be utilized in that technology. Now, in addition to the three major divisions, metals, nonmetals, and metalloids, we can also divvy up the periodic tables into columns and rows. The columns we call groups or families. The rows we call periods. The groups and families are the columns and what they will share is the chemical and physical properties as we showed in the periodic law. Another couple of distinctions we can make for looking at a modern periodic table would be the main group and transition elements. As we'll see in the next slide, the far two left columns and the far right 6 columns are known as main group elements, and we can give them an A distinction next to their column number name, and the metals in between are known as the transition metals, and we'll give them a B distinction when we use that terminology. The bottom 2 rows, which you see, actually belong in period 6 and 7, but just as a matter of convenience, making the periodic table fit on a sheet of paper or on a screen, they're sort of excluded to the bottom so that the periodic table can be a little bit narrower. Those 2 rows, the elements that are contained in them, are often called the rare earth elements. And here we have an image of the sort of top half of the periodic table. You're not pictured are the 2 columns, or excuse me, 2 rows that can make up the rare earth elements. But here we can see the group number for each group, and then of course the period numbers on the far left side of the periodic table. You can see that we've numbered the groups 2 different ways. 1 through 18 you often see on the periodic table, and that's just giving each group its own distinct number. In addition, we can also use the A and B distinction to differentiate between the main group elements and the transition metals in the middle. If we do that, group 1 and 2 become 1A and 2A respectively. It really changes when we take a look at groups 13 through 18. They become 3A, 4A, 5A, 6A, 7A, and 8A. Okay, and that's sometimes convenient to use the A distinction when thinking about the number of valence electrons in an atom, which we'll cover shortly. Okay, what we're going to do next is take a look at a couple of different groups, important groups in the periodic table, and just discuss them briefly. Now, it turns out that although hydrogen isn't a group all by itself, it is an important distinction to notice that hydrogen does not share a lot of characteristics with the other group 1 metals. First, it's a nonmetal. It's a colorless diatomic gas, as opposed to the rest of the group 1 metals being solid. It has a very low melting point. Of course, it's a major component of water, H2O. Anytime that you have a compound that can produce a hydrogen cation in solution, we're going to call that an acid. And all halogens, which will abbreviate X, which we'll see in a second, also form acids. A very important topic which we will cover in the future of this course. The rest of the group 1 elements are actually known as the alkali metals. And most of them are pictured here: lithium, sodium, potassium, rubidium, and cesium, as well as francium below it. They're all very soft metals, and they all form positive 1 cations. They're all very reactive, and they will produce bases, hydroxides, when they do react with water. Over on the other side of the periodic table, we have group 17, or group 7A, we have collectively known as the halogens. So most of them pictured here: fluorine, chlorine, bromine, iodine, astatine. They are all diatomic, meaning they occur in nature as I2, Br2, 2 atoms of the elements bonded together. They're also very reactive and very toxic to us. A lot of them are, I guess, fluorine and chlorine. They all will produce acids when combined with hydrogen, as we previously said. And one of the things that we'll discuss is that the strength of the acids is a characteristic, follows a characteristic pattern of the group. Okay, so the last group that we are going to discuss would be the noble gases, and they're on the far right side of the periodic table of the elements. They're in group 18, or group 8A, as we said. All of the gases are, all of the elements are gases at room temperature. And a very important note is that they are all very unreactive, or inert is another word for that, meaning that they do not react with any other elements or any other molecules under even the most extreme experimental conditions. It's very hard to remove or add electrons to the noble gases. 2 examples that you're probably familiar with are neon, that you often see in neon signs, of course, and then helium. You've probably held a helium balloon at some point in time, or, of course, they're used in blimps. So as we progress, we're going to want to figure out why atoms react the way they do, why they form ions the way they do, and as we'll see, one of the underlying themes that guides chemical processes is that the atoms or molecules almost seek a stability in the process of a reaction. And it turns out, since the noble gases are the most stable elements, practically inert, of the periodic tables, when we compare and contrast elements to the noble gases, it turns out that we're going to be able to learn a lot of information about why things react the way that they do.